Yo, Chuck.
What the chuck is up, YouTube? In this video, we're going to be going over Leetcode 287, find the duplicate number. The thing that stands out to me about this problem is the constraints are pretty intense. So we start with an array of integers containing n plus 1 integers in the range of 1 to n inclusive. So what does that mean in English? That means if the highest value in our array is 4, we're going to have 5 elements in our array. So that would look like this. So here we have 4 as our highest value, and then notice we have 5 elements. Because of the pigeonhole property, which states that if we have X amount of pigeons and there's not enough holes to fill those pigeons, then we know we're going to have an intersection or a duplicate value. In this case, it could be 2, it could be 2 1s, for instance, and the array is probably not going to be sorted as with the problem statement here, but just know that there's always going to be a duplicate value. Likewise, if the highest value in our numbered array was 5, we would have 6 elements in our array, so something like this. 6 elements. We wouldn't actually have a 6 because remember, we're just going to 1 to n inclusive, so that would be where we would slide in our duplicate value, okay? So that is how the numbering system works here and how that is explained. Notice also with our constraints, we're unable to modify the array of nums, so we can't sort this list of numbers to help us find the duplicate. That's going to make it a lot harder. Also, we can only use constant extra space, which means we can't make another array to, for instance, we couldn't just scan our numbers and then push our duplicate into another array, for instance, and return that newly created array. So that also makes it quite challenging. Okay, with that said, I'm going to show you the trick to this problem. There is a definitive trick, and let's go over and hop to the code right now. Alright, so you see I've copied the function from the problem, and we have a array, and it looks like it's duplicated on the value 3. So how are we going to approach this problem? Well, the way you need to approach it is you need to set a pointer to fast and a pointer to slow. So what I'm going to do is just make a variable called slow, initially set it to index 0, and then also make a pointer called fast and set that to 0 as well. The idea behind this problem is you're going to have a slow pointer which traverses your array 1 node at a time, and then you're going to have a fast pointer that traverses 2 nodes at a time. So when I say node, I'm just referring to an index of your array. So I'm going to make a while loop, and I'll set it to some condition that will always be true. And I'm just going to update the values of my pointers in this function. So I'll say slow equals nums at slow, and then fast will traverse 2 nodes, whereas slow is just traversing 1 node. Fast will traverse 2. So notice I'm doing the same thing, but then now I'm actually passing the value of that first node traversal into my indices, or my index, and that's going to make me go twice as fast, okay? And then I'm going to say if slow equals fast, I want to break. Okay, let's run this code, and I'm actually going to return slow just to see what it is. And let me clear this because I was messing around earlier, but let me just run this code, and it looks like we're coming across 3 on the number that we meet at. Let's make sure that fast is also 3. Okay, so what does this mean? They both equal 3, but what does that mean? Well, again, the slow pointer is traversing 1 node at a time, and the fast pointer is traversing 2 nodes at a time. Conceptually, it's pretty easy to understand how the slow node is progressing through our array, but it might be kind of confusing to understand how the fast pointer is traversing. So I want to write it out for a second. So imagine we start at 0 with both pointers. Slow is going to be 1 at index 0, right? And then fast is going to be 1 at index 0, but then it's actually going to be 2 because we're traversing 2 nodes. And that's that nested index value we have here. So we start at 1 because we're at index 0 with both pointers, but fast will actually take the value of that initial 0, index 0, and then go to the next one over, which is 2, because 2 is at index 1. So that's kind of tricky, but you can kind of see the logic there. So let's keep going. So now we're at value 1 at slow. If I go to index 1, that's actually 2 now. So I'm going to go to 2. Fast, I'm starting at index 2, which is 0, 1, 2. That's 4. And then now I'm going to go to 4, index 4, which is 3 right here. So I could say 3. And then slow, I'm starting at index 2, so 0, 1, 2, which is 4. I'll say 4. And fast, I'm starting at index 3, which is 3 again. And then I'm going to 3, which is 3. So notice I'm kind of like stuck on 3 now with the fast pointer. And I'm going to start at index 4 with slow. So if I go 0, 1, 2, 3, 4, that looks like it's 3. And then with fast, I start at index 3, so 0, 1, 2, 3. And then 3 is telling me to go to 3 again. So I'll be at 3, so 0, 1, 2, 3, which is also 3. So at this point, they're equal to each other, and we're going to break out of the loop. So let's console log that to prove that this actually happened. So I'm going to console log slow and pass in the value of the slow, and then also fast and pass in the value of fast. So if I run this code, you can see the logic we just had. It's not showing you the last transformation, but if I put the console log statement down here, you can see where we align, right? So what's happened here is we've actually created a cycle or a loop. This problem is called Floyd's cycle, or it's called like the tortoise and hare. I don't know if that's probably not how you spell tortoise, but it's a known problem where you end up having a loop, and these values will keep looping forever on each other because there's the pigeonhole problem, like we talked about before, where because there's a duplicate value in this length of array. Remember, our max value is 4, and we have 5 elements. Therefore, there's going to be a duplicate. That duplicate causes a loop or a cycle like this. So obviously, we're breaking at 3 because that's where they equal each other. And if we didn't have that case, this would go on for infinity and then would crash our computer, right? But let's keep going outwards and seeing what would happen if we keep going with these pointers. So fast is just stuck in this infinite loop of 3, 3, 3, 3, 3, right? With slow, I'm at 0, 1, 2, 3, which is also 3. So slow actually got caught in the same loop and the same cycle, and it's just going to repetitively do 3. So here's where the magic of this algorithm happens. Now we have captured the node where there is a cycle, and that is what we need to solve this problem. So I'm going to make another pointer now called init, and that's also going to be set to 0. Notice that slow is set to index 3, right? It's still set to index 3. Let's remove this console log statement. So I'm going to do another while loop. Same idea. I'm going to have a condition that's always going to be true, and it's always going to be firing. Now, I'm just going to copy this slow code, or the slow logic, which traverses just one node at a time. Remember, fast traverses 2, slow just traverses 1. And then I'm going to do the same thing for init, and I'm just going to traverse one node at a time. And I'm going to say if slow equals init break. Okay, now if I return slow, what happens? We get our duplicate value, right? So this is pretty much the answer to the problem, but what is happening here and why does this work? Okay, so you got to understand that slow, the first loop we did was just to determine the node in which there is our cycle. We want to find where the cycle starts, and that is at index 3 as we've established. Init is just starting like slow did initially and working through the array. So let's walk the dog and see what these equal. It should be pretty easy because they both are traversing one node at a time, so it's not really that confusing to see what value they become. But let's say we've got 3 and 0 at the start. So if I go to index 3, that's 0, 1, 2, 3, that's 3, and it's just going to go 3 forever, right? With init, we start at index 1, and then index 1 is 2, and then 2, 0, 1, 2 looks like it's 4, and 4 is 0, 1, 2, 3, 4, which is 3. And here we have our connection where they both meet, right? So the interesting thing about Floyd's algorithm is that it basically knows that if you start at the node, which is the cycle, and then you have another pointer start at the beginning of the node list, they're eventually going to hit each other. Because remember, this is a loop where slow is stuck on 3 forever. It's just looping on 3. So eventually init is going to cross paths and collide with the slow. Like imagine a graph where 2 lines intersect. That's the same idea here. So this problem is has a time complexity of O of n. It's linear time. But the constraints of this problem make it so you pretty much have to use this algorithm. This problem is tailored for you to use Floyd's algorithm, which I think is kind of unfair because if you were never exposed to this, chances are you're probably not going to solve this in linear time of O of n. So that is the problem itself. I hope you guys enjoyed this video. If you found it valuable, please be sure to like and subscribe. Again, it might be kind of conceptually confusing to understand this logic at first, but just know that that first while loop is just to grab the location or the node or the index of the start of the loop. And then the magic of Floyd's algorithm is that now that we know the start of the loop, we can traverse one node at a time with both pointers, and they'll actually end up hitting each other. Truly incredible. Okay, thanks for watching, guys. I will see you in the next one.